KL divergence and duality. Most of our models will be maximum entropy models with constraints, but maximum likelihood is a really nice tool for working with data. KL divergence includes both as special cases. So we're going to start looking at probability distributions with weights or parameters. So each P in our probability vector, bold P, depends on some weight vector. This is called a parameterized model, and the weights are called parameters. Logistic regression, for example, we have a sample space with two outcomes, and we have this conditional probability that y is t1 given the observation of the x's and those weights. And the weights means that this is actually one component of a two-component probability model. It's the one for t1. For t0, we get p0 of w, which is 1 minus p1 of w, which looks like that. And p1 and p0 together constitute the probability vector p for two possible outcomes that we call logistic regression. So maximum entropy means we don't have to make assumptions about form. They're the best models in the sense of being maximally uncertain given the constraints. So our maximum entropy model is to find the argmax of the entropy subject to the constraints. There's the definition of entropy. We use a Gibbs form, which is an exponential form. The weights are in the phi sub i's that are in the exponents, and the sum of the exponential terms is called z, the partition function. But other than that, maximum entropy does not require explicit definition or some kind of exact specification of phi sub I of w. And this is very important because in data science and machine learning, we're often working with very complex multi-layer models. And we base our machine learning applications on architectures rather than on explicit forms. And we tend to optimize over the weights. So when we find P star as the argmax of the entropy, then the variables are these weights. The Gibbs form, again, means that our Lagrangian is negative of sum, that's the entropy term on the first, plus those are the constraints. And the solution satisfies that the derivative with respect to each weight w sub j in the weight vector of the Lagrangian has to be 0. We often use expected value constraints, which look like this. And that means we're looking at where this expected value summation is equal to b sub k. And let me explain. This f sub k is a function from the sample space to R, and it's a function of y, the variable. Notation here, we're saying f sub k of y, but actually we mean f sub k of t of y. We've done that many times now. So this is the expected value of f sub k of y, and with respect to the probability distribution p that we eventually are going to solve for. Now often the b sub k is the expected value with respect to another distribution, one that's given to us before the problem, and very often it's an empirical distribution, a distribution derived from the data. So in that case, the b sub k would be this exponential with respect to p tilde of these functions, and so our expected value constraints look like this. And our Lagrangian correspondingly looks like this. But we seldom use entropy directly. In particular, suppose y is associated with a set S of R outcomes, and we have our probability distributions on our R outcomes. Pure entropy defined this way, cross entropy this way. We're going to use NATS in this video. This is our KL divergence, and we tend to use KL divergence instead of the entropy. Maximum entropy is going to correspond, as we'll show in a minute, to minimum KL divergence. And notice that the KL divergence is a function of both P and Q. So let's illustrate. This is our KL divergence. We proved a theorem saying it is non-negative, and it's equal to 0 when the P and the Q are the same distribution. So the KL divergence in terms of the logarithms looks like this. This is a convex combination of convex functions of p, which means that the KL divergence is convex in p, and we get a global minimum as a function of p. But likewise, the second derivative with respect to q of that first term is positive, which means that we also again have convexity in q and a global minimum as a function of q. So a uniform distribution actually maximizes entropy. Let's look at that. Here is KL divergence for P with a uniform distribution. And we've got a negative and a log base 2 of 1 over r, so that becomes just log base 2 of r. And then we take the log base 2r out. The sum of the p sub y's is 1. So we have just log base 2 of r minus the entropy. And it has to be greater or equal to 0. So for all probability distributions p, the entropy of the uniform distribution is greater than or equal to the entropy of p. That is, p star is the argmax of the entropy if and only if p star was the argmin of the KL divergence. But what about KL divergence for a Q other than the uniform distribution? And we often rely on Gibbs forms and Lagrangians for the work that we do. Here's our Gibbs form. Take the logarithm on both sides, and notice we get the log of p sub y of w is phi sub y of w minus log z. So our Lagrangian is going to simplify to this form when we substitute in for the logarithm of p sub y, and we can separate the sum, and there's no y's in the log z, so we just get the sum of the probabilities, but that's equal to 1. And so we have this as our Lagrangian in terms of the Gibbs form. And we also get a simple calculation that the partial p sub I with respect to w sub j is equal to this, which is p sub I times, in the parentheses, the partial phi sub I with respect to wj minus 1 over z, the partial of z, the partition with respect to w sub j, component of the weight vector. So if I have y associated with a sample space S of R outcomes, and I have two probability distributions on R outcomes, P and Q, well, here's my KL divergence. I'm writing the Q's in magenta so we can track them. And notice that the definition gives us a negative negative and P sub y common to both, so we simplify that. The associated Lagrangian is given as you see here. And we're going to introduce a new Gibbs form. P sub y equals 1 over z q sub I e to the phi sub I w, where z is the sum y equals 1 to r q sub I e to the phi sub I w. The derivative doesn't change. It's the same as for the old Gibbs form. And notice that I get log p is equal to the phi sub y of w plus the log of qy minus log of z. And I will get some cancellation when I substitute for the log p. In particular, I end up with this. And if I simplify in the same way as before, then I actually get something very similar to the Lagrangian for entropy. In fact, if mu sub k was equal to negative lambda sub k, they would be the same thing. If p star is in the set of probability distributions in R space, if the derivative with respect to w sub j, the jth component of the weight vector, of the KL divergence Lagrangian is 0 at p star, then the derivative with respect to w sub j of the Lagrangian for entropy at p star is also equal to 0. Now, convex functions have unique minima, so therefore the argmax of entropy is the argmin of the KL divergence. And we tend to call this q sub y a prior distribution, and we tend to denote it using a p tilde of y instead of just the q. Why? Because p tilde of y is often an empirical distribution. So KL divergence is often called the information projection of the distribution P onto the prior distribution P tilde. So we have a new maximum entropy model, which actually is minimizing the KL divergence in the first argument with respect to the constraints. And notice that it would reduce to the ordinary if we used uniform priors. And our solution is going to be in a different Gibbs form, a new Gibbs form that has this prior in it. But what about minimizing the KL divergence with respect to the second argument? Well, now we go back to our likelihood functions. So remember, a likelihood function is motivated by the joint probability of y1 being little y1 for trial 1 and y2 being little y2 for trial 2 and so on, which gave us this, because they're independent and identically distributed, it gave us this product form for the likelihood function. Zero probabilities do not produce trials, so we assume that S is just the set of all outcomes in the trials, and that would mean that none of these probabilities can be zero. So here's our likelihood function. We're going to make it a log likelihood function by taking the logarithm. And then using our exponent rule for logarithms, we can factor the m's to be coefficients of the logs. And write that in summation notation. So the natural log is an increasing function, so the argmax of likelihood is the same as the argmax of the log likelihood over the weights. And so we have what's called the maximum likelihood problem, maximize over the weights W, the natural log of the likelihood subject to the sum of the probabilities is 1. In other words, this problem. So our goal is probability models depending on these weight vectors. And our maximum likelihood problem is what we use to find them. Now, we're going to use a Gibbs form, the old Gibbs form, but notice that the sum of the p sub i's is 1, so we've already satisfied our constraint. And we can replace the log p sub I in the summation remaining, and we end up with this. And we're going to call that a function h, and we're going to take the derivative of h instead equals 0 because we're trying to maximize likelihood. Notice that for our derivative of the partition function, we have something that looks like this. The derivative of h with respect to a weight coefficient is equal to this sum minus m over z, the partial of z with respect to w sub k, because derivative logarithm. And notice that's going to be, when we distribute the sum, something looks like that. Notice we've got a 1 over z e to the phi sub I of w in the second summation, but that's just p sub I. So if we set the derivative of h equal to 0, we get that these two sums have to be the same. And notice I can divide by m, and I'll get the m sub I over m, but that's our empirical distribution. Now let's re-index in terms of y, just so it looks like what we saw earlier. And notice we can define functions from S to R by f sub k of y is the partial phi sub I with respect to w sub k. Substitute that in, and we have expected value constraints. So in other words, if we have our maximum likelihood problem, the solution satisfies expected value constraints. But notice that I can factor out an m and divide by an m inside the sum, and that's going to be my relative frequency, the counts over the number of trials. That's my empirical distribution. So now I have this, and I'm going to change this to minimization by putting a negative in front. But notice that I've got a negative sum of one probability distribution log the other probability distribution. That's cross entropy. So the maximum likelihood problem is a special case of minimizing cross entropy subject to the sum of the probabilities equals 1. Notice now that if this is our equivalent problem to maximum likelihood, that the KL divergence is defined this way, and therefore the cross entropy is the KL divergence plus the pure entropy, but the pure entropy of the prior distribution, which tends to be empirical. It's constant. We're given often the empirical distribution in an explicit form before the problem. So that means that finding the argmin of the cross entropy is the same as finding the argmin of the KL divergence in the second term. So here's our equivalent problem. Minimize the KL divergence of the empirical distribution with respect to p in the second term, subject to our sum of the probabilities is 1. In other words, maximizing likelihood is the same as minimizing KL divergence over the second argument, but maximizing entropy is the same as minimizing KL divergence over the first argument. Now, KL divergence of p tilde with respect to p is not the same in general as the KL divergence of p with respect to p tilde. However, notice that we have this problem, our maximum likelihood problem equivalent to it, and this maximum entropy problem, and we get the first problem satisfies the expected value constraints, and so therefore if the constraints for the maximum entropy problem are these expected value constraints, what does that mean? We get the same argmin distribution for both. So we end up with the best of both worlds. Maximum entropy models use constraints rather than explicit definitions of functions, no assumed models, but likelihood is flexible and pragmatic. Here's our maximum likelihood problem with summation notations. And especially, what if we transform the maximum likelihood problem into sums over individual trials? So to get likelihoods over individual trials, we use what's called an indicator function, which is defined here. And that allows us to write this single sum as a double sum, but notice now we've got an I equals 1 to m over the trials, because the indicator function will be 1 exactly m sub j times in the inner sum. Let's look at an example. So suppose I have y1 to y10, and the trial outcomes, which are in S, look like this. Then notice I've got m1 is 3, m2 is 2, m3 is 2, and m4 is 3. So when I look at this double sum, what happens is I can switch the order of the summation, and then I will get exactly m sub j and be summing j equals 1 to 4 over the outcomes of S. If we look at this for our example, notice we have for each I, only one term is non-zero because you only get one outcome per trial, and then you get something like that. In other words, likelihood is represented per trial. So we have the flexibility of the maximum likelihood problem, including over individual trials. What about if r is equal to 2? So our sample space S for r equals 2 is t0, t1, but it's advantageous to use instead the sample space 0, 1, because then our indicator functions are quite easy. The indicator function of 1, if y sub I is equal to 1, then it's just an indicator of itself. Likewise, if y sub I is equal to 1, then the 0 indicator function would be 1 minus 1, which would be 0, and vice versa. So here's our maximum likelihood problem, and we take the inner sum and write it over the outcomes 0 and 1, and now we substitute our indicator functions, and our p is equal to p1, and so p0 is 1 minus p, and notice we now have what this is called a binary cross entropy loss, which will be very important in many applications. In other words, maximum likelihood, minimum divergence, we have all these equivalent problems, including a very nice way of looking at binary cross entropy loss in association with all these equivalent forms.